Welcome back to our engineering mechanics lectures, and now we're looking at our next topic, which is actually a continuation from before, where I want to talk about parallel force components through the so-called scalar product. And the reason this is a continuation is really because we are looking at a method that can be used to determine the angle between two vectors. That is where we left off our lecture last time when we talked about position vectors, and now we're going to provide a method for analyzing the angle between two position vectors, if you will. We can also use the method that we're going to use today to understand how to calculate parallel force components in structural members. So therefore, I want to introduce the concept of parallel and actually perpendicular force components. But the method that we will look at today is really only meant to calculate parallel forces. And you will understand that as we move through it, because of our ultimate goal, which is to calculate these force components in actual structural members. So let's put that to an application, or first let's really talk about how to get there before we put it into application. And so therefore I want to introduce to you the scalar product. And the scalar product is a better name than what most of us actually know this by, which is called the dot product. The dot product is what we called it in high school, but I really like the term scalar product because it will always allow me to find the right magnitude. So this will tell me that this result here is never a vector. And the reason I say that is I often see that go wrong when students use this method. I ask them actually not to use the scalar product, but I ask them to find the parallel force component, and then somehow magically they come up with a vector. But if you memorize that this is called the scalar product, and scalar stands for just a single number, then you know that you have to come up with a magnitude and not with a vector. You can vectorize it, as I will show you later, but you by default will always find a magnitude and a magnitude only. So please keep that in mind, that we use this in this class just to find vector lengths, if you will. And not component. No components. But components are derived through other methods. So those other methods are just an extension of what we're going to do with the parallel force components or with the scalar product. So now let's talk about the definition of the actual scalar product, or the rules that we all learned in high school before. We probably remember this, but we should have it here anyways. So first of all, the scalar product is really defined, or the scalar product between A dot B, and so this is often written as A dot B, and that is defined as the product between A and B, or of A and B, precisely the magnitudes, and then multiplied by the cosine of the angle between those two. And the reason I left some space here is because it has to be the smaller angle between the two. So let me explain that a little better. So for that we have a short drawing here, or a small drawing. And let me draw two vectors, vector A if you will, and that is crossed by vector B. And now those two vectors have angles to them. So let's call this theta 1, and we call this theta 2. And when I ask the students in the classroom now, they tell me, clearly it's theta 1 because it must be the one between A and B here. And then I say, okay, that sounds good to me if you argue that way, but what really happens if I change the direction of A? So let's say I point A in the other direction, then the angle between those, according to the logic that the students give me, would be theta 2. And that cannot be true, really, according to the definition, because, spoiler alert, when we talk about the laws of operation, we will find that A dot B is equivalent to B dot A. And so theta 1 obviously is not as large as theta 2, and therefore that does not work. So it is not the angle between the two arrowheads that would be not true to the definition. It actually has to be the angle that is the smaller one of the two. And so the smaller one here would be theta 1, but that we will write down in a second. Let's first write down the actual law, which is A dot B is equal to A magnitude times B magnitude times the cosine of theta. And that theta, again, needs to be less than 90 degrees in 2D, of course. This is in 3D, this is a little bit different. But the concept here is easier to visualize in 3D. And this is a very important rule, so let's highlight it and let's memorize this. I will get back to this throughout the lecture today. So memorize A dot B is equal to A magnitude, B magnitude, cosine of the smaller angle between the two, here called cosine theta. So now we are ready to talk about the laws of operation, and I already gave you a small spoiler alert, but that law of operation is really called commutative law. So let's write that down, the commutative law. And that sounds fancy, but really all that says is that A dot B is nothing else than B dot A. That is defined that way, and you will see in a second why. And since we're talking here really about a multiplication, let's talk about multiplication with scalar next. You probably remember this from high school, that if you have a scalar A and you multiply it by A dot B, that this is equal to A multiplied by the vector, and then you dot it with B. Or likewise, it's also equal to A dot AB. So this is all the same, and that is the multiplication with scalars. That leads us to the distributive law. So this has something to do with how you do multiplication and addition. So distributive law, which states that if you have A vector and you dot it by B plus C vectors, that is nothing else than A dot B plus A dot C. So it's kind of like regular multiplications, if you want to think about it this way, like multiplication and addition. And so these rules apply no matter what you do with your vectors. And now I want you to think about this in terms of our base vectors. So remember that we had I, J, and K. So I, J, K hat. And those were our unit vectors. And if I write those in our old form, then remember that I is 1, 0, 0. J is 0, 1, 0. and k would be 0, 0, 1. And again, our old form that we don't use from now on anymore is this form. And remember the formula, right? Remember that a vector dot another vector, so a dot b is really equal to a magnitude b magnitude cosine of the angle between the two. And so now think about that, what that means for these vectors. What is the angle between them? They are defined by being mutually perpendicular to each other, and so the angle here is really 90 degrees. So the angle between them, so angle between I, J, K is really, for all of them, 90 degrees, right? And the cosine of 90 degrees is what? Is nothing else than 0. So in other words, if you have I dot j as the base vectors, you will find that that is actually equal to 0. And likewise, I dot j is also equal to 0, and j dot k would also be equal to 0. So now the question then is, what happens if you dot I, and here comes my expression, onto I itself? So I dot it onto each other, or actually, as I would call it properly, projected onto each other. So then you have an angle of 0 between the two, right? So the angle between these two would be 0, so theta would be equal to 0, and therefore the cosine of 0 is equal to 1. And then you find that I dot I is nothing else but 1. And that is an important concept to understand. And again, this goes actually back to our unit circle that is like listed in your very first lecture, where we didn't even have a video about because it's so basic, but please understand that it's derived from here. Similarly, j dot j, of course, is equal to 1, and k dot k is also equal to 1. And the reason I'm actually expanding on this is because I want you to understand what that means for a dot b. So remember that a dot b is actually defined as we did before, and you probably remember this formula from high school in a different way, or in an additional way, I should say. So you may remember this as ax, which we write as I hat, right, and ay j hat plus az k hat, and now I'm going to dot this onto bx I hat plus by j hat plus bz k hat. And now if I do what I learned in high school, where I combine the terms properly, I would be able to rewrite this as something like ax bx I hat dot I hat plus ax by times I dot j plus ax bz times I dot k. And that was the first multiplication, right? So if you want to think of this. So I took ax and multiplied it by bx. I took ax and multiplied it by by, and I took ax and bz. And so now this is like simply like multiplication, and I'm going to do the same for this component now and for this component, so I have them all multiplied through. I'm not going to write them all, but just to give you an example here. So then I would have plus ay bx, and that would be j dot I, and then I have ay by, and this would be j dot j, and then I have A, Y, B, Z, and that would be J hat dot K hat. And I guess I'm just going to complete it now. So last but not least, I have AZ, BX, and that would be K dot I plus AZ, BY, K dot J plus AZ, BZ, and then K dot K. And so once again, what I did is just multiply it like we are used to from high school. And the reason I did this is because now I want to apply these rules up here. So I and j becomes 0, and j becomes 1, for example. So what does that mean for us? That means that this here now becomes 1. This becomes 0. This becomes 0. This becomes 0. This turns into 0. This turns into 1. This turns into 1. And then we have 0 and 0. And so what you will find now is that only in this case, because of the way I wrote it, the diagonal terms actually remain, right? So these terms remain, and that leads us to the formula that you know from high school, which is really nothing else than A dot B is equal to AX BX plus AY BY plus AZ BZ. And that, again, is another formula you definitely want to memorize. You probably already memorized this from before, but it is something that you need. And now I derived it for you so you know where it comes from. And I will show you in a second why it's so useful for engineers. But again, highlight and memorize this. So this formula can be combined with our other formula. In fact, let's zoom out here and talk about the combination of those. So what I will do now is I will look at this formula together with this formula to find a useful application for engineers. But this is the laws of operation and the general concept for the scalar product. So now that we have an understanding of the formula for the scalar product, let's talk about actual applications or use cases here. So I want to talk about two very specific ones that usually are applied in engineering. So the first one would be to find the angle between two position vectors. So find angle two position vectors. And how do I do this? So for that, I just need to use the two formulas that were just given to you, right? And so I'll repeat them. A dot B is nothing else than A magnitude, B magnitude, cosine of theta. But it is also equal, remember this, it's also equal to AX BX plus AY BY plus AZ BZ. So I can set them equal and really solve for this angle, right? So all I have to do is bring these over to the other side so that the cosine of theta, so cosine of theta is really equal to AX BX plus AY BY plus AZ BZ. And the whole thing divided by A magnitude and B magnitude. And remember that the magnitude of a vector, or even in 3D, is just the Pythagorean theorem, right? So I have ax squared plus ay squared plus az squared, and then square rooted. And remember, this is then multiplied by the b magnitude, which is bx squared plus by squared plus bz squared. And that also is just square rooted, so that the formula now applies, and now I can find the angle between two vectors. That is something very useful for engineers. If you have two position vectors given, now you can find the angle between them, and I believe that we don't have to really exemplify this or elaborate on this. I believe this is very doable. However, what's often new to beginning engineering students is the second part, which is to use the dot product or the scalar product to project one vector onto another, or I should say to really find a component, a parallel component. So to find parallel force components. And the way that works is you use the scalar product, so use scalar product to project, and project is a word that I use, one vector onto another. But the another vector needs to be technically a unit vector, right? So it needs to be unit vector. And you will see in a second what I mean by that, but please understand that this is important for now. Because if you do not project the first vector, let's say A onto B, and you do not use the unit vector for B, then you actually multiply the magnitude by vector B. I guess it's better if I write that down. So let's say you have A dot B, and you're looking at two vectors. Let's make a small drawing of that. So let's say you have A here and B there. So A vector and B vector, and of course we know that in between we have the angle theta. And remember that I write it once again, A dot B, so that we won't forget this, cosine theta, right? That's really the definition of the dot product. And really what this does, right, is you take the cosine of A and theta, if you will. So what do I mean by this? Let's say I know the magnitude of A, which is the length from here to here, and then I multiply that by cosine. Let's forget about the B for a second here, but let's say I multiply this by the cosine of theta. What do I really get? This part here, right? So let's say there's a 90-degree angle here. This component here, this is really A magnitude times the cosine of theta. So the B is actually a multiplier in this case. So you can think of B as intensifying this component. So what engineers like to use the scalar product for is to find parallel force components, or like parallel components, if you will. So how much of A is parallel in B, if you will. And that's why I call it projection, the dot product, because you really project this force onto this baseline here. And one way to make that happen is, instead of using B, you actually use the unit vector of B. So what would that be, the unit vector of B? So you remember that a unit vector is always a vector that is parallel but has a length of 1. So let's call this vector B hat. So how do I get B hat? B hat is nothing else than B components, or the vector divided by B magnitude. So that ultimately, if I want to find a parallel component, so to find parallel component, to find the parallel component, all you have to do is to say that A magnitude times cosine theta is multiplied by B divided by B magnitude. So that would really give you the parallel force component. And that is something that initially seems a little bit overwhelming, but a short problem for that will be shown to you in just a little bit so that you can practice that. Before we do that, let's show one more case or one more application here, which is very similar to this. And for that, let me draw, or let's actually write down 3, which is finding force components along x, y, z axis. So for that, I think a picture is better than anything else. So let's draw a 3-dimensional coordinate system. Let's do that right here. So I have a 3-dimensional coordinate system. And usually we have x, y, and z. And let's place a force in it. So let's say the force is acting in this direction. And we, of course, understand already the directional cosines and things like that. But for visual representation, I need those lines anyways. But let me just show you that, for example, here I have the angle beta. Remember that? That's between the vector and the axis. And now if I include my base vector, which on the y-axis would be nothing else than j hat. And so now you can imagine that if I have, let's say, a vector here, and let's call that f vector, so I can find fx, right, fx by dotting it onto I. So by fx is nothing else than f vector dot onto I hat. And that will give you actually the value of the x component of that particular force. Why is that? Because you would just have something that is f magnitude times 1, right? Because that's the unit vector, times the cosine, in this case, of, well, actually, in this case, it would be alpha because I'm talking about fx here, right? So here I set fx, and here I use beta, so let me fix that, or let me write that as well. So fy would be equal to f dot j, which then would be equal to f magnitude times 1 times the cosine of beta. And for the last angle here, gamma, it would be the same concept. So you can always use the scalar product to find certain components. So let's talk actually about case 2 and case 3 here, because those are very identical to each other or very similar to each other. You always find the projection onto an axis or onto another vector. And this is visualized here for 2D, but it works wonderfully in 3D as well, as you will see in an example in a second. But to complete this, there's not just, of course, a parallel component, there's also a perpendicular component, and similar to this concept here. So let me actually draw the missing line in here that we, of course, remember from our last lecture. So that the angle there is actually in a plane that is spanned, like here is the end of the plane, and then we have technically a right angle down here. So that means that this here would be the part that is perpendicular to the y-axis in this case, right? So that's similar to what's going on here. This part is perpendicular to this part. So how do you get this? You can, of course, use other mathematical vector operations, but that's not the point of today's lecture. The point here is to actually recognize that we're looking at a right triangle where the hypotenuse in this case is A, right? So this is the adjacent and this is the opposite. So you can, of course, use the sign then for this side, if you will, but you can also use Pythagorean to take this side squared minus this side squared. So for example, let's give that actually a name here. Let's say this is h, the height, and so h squared plus, and now I'm going to use what I wrote there, a cosine theta, and that squared is equal to a squared, right? That's what that means. And then down here, where you have the perpendicular component, you can also say that perpendicular component squared is equal to f squared minus the component that we wrote down here. So minus, let's see, f magnitude times 1 times the cosine of beta, and that also squared. So in other words, this is all Pythagorean, what I've just done here. So this is Pythagorean, this is how you know it, a squared plus b squared c squared, if you will. And here I solved it like so. Here's my hypotenuse, and here's a component, here's a component. Whereas the hypotenuse in this part here is up here. But that, I think, completes how you can look at these scalar products and how do they relate to each other. And I believe now we are ready for an application and a problem statement. So let's take a look at our first example for the scalar product. And first things first, we always need to read. So here it asks you to find the parallel force component in AB due to the 300 Newton force, which is acting parallel to the XY plane. So let's take a look at this picture here. So this force here, 300 Newton, is only parallel to the y-axis, and it's acting in the XY plane, if you will. So there's no Z component, there's no X component either, but the force is acting parallel to the XY plane. And then you have this structure here from A to B, and there are some legs attached, but they are not even marked. Let's forget about them. In fact, if you read this note here, it tells you to ignore the legs of the tripod. Technically, that can lead to complications in terms of how the load is distributed throughout the structure, but that is not our concern here for beginning engineering mechanics. That's not our worry. In the real world, it would look a little bit different, but let us just consider pipe AB here, which moves from 0 z-axis to a height of 3 meters. So that is obviously not parallel to this force. No matter how you look at this problem, this force is acting in the XY plane, or better I should say, parallel to the XY plane, and AB is slanted or sloped upwards, and it's not acting in any plane that we see here. So that means that we have to understand a very important concept, which sometimes, based on my experience in the classroom, is not easily understood by students. But maybe I can zoom in a little bit for you and make you think about this. So I want to identify pipe AB for you here, which once again is not parallel to the force. So what that means is that we actually, if we extend that pipe, which I'm going to do here now for you, there is a triangle that the pipe forms with the force. And if I want to complete that triangle, let me draw the perpendicular component to it. So I also have this part here. And so now I have 3 parts, which is technically vector decomposition, or is nothing else than vector decomposition. And what we have here is first the 300 Newton, which is in blue. And then let me call that F1. So now I can determined that there must be an F1 that is parallel, right? So, and technically that should be F1 and then the sign for parallel is this, but I didn't want you to be confused with the 1 and the parallel sign. But you also understand that there's F1 perpendicular. So that is a concept that needs to be really visualized by engineering students. They need to understand that a force that is not acting parallel to a member always produces two components. It produces a force component that is parallel and one that is perpendicular. Let's not really worry about the perpendicular one right now. I know that often students get confused about this initially, but we will talk about this later, and actually we'll talk more about this in follow-up classes, because one confusion that always comes is like, in which direction is this really acting? Is this acting away, or like, is it acting towards me? Is it acting away from me? Is it acting in a random direction? Is it defined? Those are things we are not worrying about. What we are worrying about today is the parallel force component. And you probably already understand that there's an angle between these two. We will not worry about this angle today, but you know that there's the angle theta here. And so therefore you understand that you can actually project effectively this force onto this extension of the structural member. And so we can really apply the scalar product now to find the parallel force component along AB. And I believe it's a good time for us to do that now. But once again, I want you to understand that we have always two components that are the result of a force acting not perfectly parallel or not perfectly perpendicular to a member. So, of course, if your force was acting perfectly parallel, then you wouldn't have a perpendicular component. If your force would be acting perfectly perpendicular, then you don't have a parallel component. But any other force, like this one here, would always produce a parallel and a perpendicular component. So let's calculate that. Because remember, I write it once again, A dot B is equal to A B cosine theta. But the question is, how does this apply in this case? So in this case, we have two vectors. We have a force and a position vector. So my force F1 is already given to me, but I'm going to write it out anyway. So F1 is nothing else than 0 I hat plus 300 j hat plus 0 k hat. And this is given in newtons in this case. And now for the position vector, let's call that AB. That is a vector AB. Now, what is that? Of course, you know this from your basic math class. In the x direction, I'm going positive 2. In the y direction, to get from A to B, I'm going positive 6. And then in the z direction, I'm going positive 3. So let's write that down. So everything is positive in this case. So plus 2 I hat plus 6 j hat plus 3 k hat. And that in this case here is given in meters. And I want you to understand now that it's a difference if I go from A to B or from B to A. And the question here asks you to find the parallel component in AB, not in BA. So be careful with that. So we're moving in this direction. But remember what I tried to allude to earlier, that the force, the parallel force here, is projected by F onto the extension onto pipe AB, right? So if you now were to apply this formula blindly, let's say the full magnitude of A and the full magnitude of B, and then you take the cosine between them, then you would pretend that the 300 has a higher impact on a longer pipe. So the longer this pipe AB would be, the more parallel force you would have due to the 300. And that is not possible physically, right? So you have to understand that the parallel force component in this pipe is only dependent on this magnitude and has nothing to do with the magnitude of AB. So what that means is that I need to find the unit vector of AB. And let's write that down. So AB hat is nothing else than 2I hat plus 6J hat plus 3K hat. And then the whole thing divided by its magnitude. And the magnitude is 2 squared plus 6 squared plus 3 squared and square rooted. And if you run the numbers, you will find that the square rooted term is actually 49, which then is 7. So we have 2 over 7 I hat plus 6 over 7 J hat plus 3 over 7 K hat. And keep in mind that here we have meters, but here we have meters as well. And so therefore our unit vector now is actually equal to unitless. And that is something that must be the case, otherwise it wouldn't work, right? So if you were to usually multiply this by this, so a force in newtons by a distance, then you would end up with what's later known as a moment, so Newton meters, and that cannot be the case because we're really looking for a parallel force component. So you need to somehow get rid of the meter here, which that is another reason why you have to turn the second vector into a unit vector. But now we can run the math, which is really not that difficult. So we now have F1 dot AB hat, and that is effectively equal to, let's write it out, 0I plus 300J plus 0K, and that is dotted onto, well, let's use a unit, dot onto 2 over 7 I hat plus 6 over 7 J hat plus 3 over 7 K hat. And that is unitless once again. And so now if you run your general concept, remember that it's just component plus component. So 0, well, let's write that out as well. 0 times 2 over 7 plus 300 times 6 over 7 plus 0 times 3 over 7. And of course, all the other numbers fade away because they are 0. But ultimately, what you will find is that you end up with 257.1 Newton. And this is actually a result. So let's mark that as a result. And let's analyze that result and ask ourselves if this makes sense. And in my opinion, it does make sense. Why? Because it is less than 300, and that's very important. That's a check you can run in your exams and in your engineering real world. You need to make sure that the hypotenuse is the hypotenuse is longer than your parallel component or your perpendicular component. That cannot be any other way. That's why it's called the hypotenuse, right? So here, my parallel component is really less than the hypotenuse. In fact, I probably should write down that this here is really F1 parallel. And that is also a magnitude. That's the other thing to understand here. So like I said at the beginning of the lecture, sometimes students magically use the dot product and end up with like something ijk, and that's not possible. So we only found the length of this vector here. And the length must always be just a number or a scalar, right? So the length can only be a scalar. So this is a magnitude. Please don't forget this. Now you may ask yourself, but we always have to give magnitude and components. So how do I get my components? How do I know exactly ijk of this force? And the answer is right in front of you here actually, because you already know the direction of this force. The direction of this angle or of this parallel component is given along this line. And what is the line? The line is given by this unit vector, because the unit vector AB hat describes the direction of this pipe and therefore the extension, which is the parallel component. So to find the F1 parallel as a vector, what you have to do is you have to take your 257.1 Newton and multiply that by your unit vector. So in numbers, that would be 2 over 7 I hat plus 6 over 7 j hat plus 3 over 7 k hat. And if you run the math here, what you will find is that you end up with 73.5 I hat plus 220 j hat plus 110 k hat. And this once again is in Newton. So now I end up with another result that is part of my answer. So I better provide an answer arrow. And in this case, I am technically done, because let's take a look at the problem statement. The problem statement asks us to only find the parallel force component. And technically, this could have been interpreted as being done here, but when you find vectors, you always give the magnitude and the component form. So let's, however, for educational purposes, talk about further implementation of this and the fact that you could, as I mentioned to you before, now calculate the perpendicular component, right? So you could calculate F1 perpendicular, simply the magnitude of it, by using the Pythagorean theorem, which would be F1 squared minus F1 parallel squared, and then the whole thing square rooted. So if you use numbers for that, what would you end up with? You would have 300 squared minus 257.1 squared and then square rooted, which, if you calculate that out, ends up to be 155 Newton. Or you can actually find the vector in this case, F1 perpendicular, by subtracting the components as well. So remember, you have 300 j hat, and then you subtract the 73.5 I hat plus 220 j hat plus 110 k hat, and then you will find that you actually end up with minus 73.5 I hat plus 80 j hat and minus, be careful, right, minus 110 k hat. And that again is also in Newton. And now if you were to take this result and you take fx squared plus fy squared plus fz squared and you take the square root of that, you will find that you end up with 154.6 or something like that, which is really almost 155. So that gets a check. And therefore, we are now at the end of this problem, and we solved actually more than we were asked for, because we now have the parallel component and its perpendicular component. And I believe this is an important concept for engineers to understand. The math, in my opinion, is often not the problem to get across to students, like many things actually in mechanics, because the math is very simple if you think about it. The problem is to understand the physical implementation that we try to derive here at the beginning of this problem. So I encourage you to really study that deeply, because you will have to set these problems up yourself. So you have to find the proper expression for F1 and for AB and AB hat. Of course, it's not always AB, like we will give you different problems, but please understand that you have to read the sketch and then turn it into a calculation. And applying the calculation is usually not the problem. The problem lies here. However, I think I stressed that enough now, but I want to mention one last thing because it's so important and I see it being confusing so often in the classroom, and that is to understand that any force that is not parallel to a member always produces a parallel and a perpendicular component. And that is something some students need to be harder convinced about than others, but please try to somehow grasp that concept. It will come later on in many, many different forms, not in the form of dot products anymore, but you will see forces that have to be broken down into parallel and perpendicular components. So this is a concept you need to understand deeply. Please make sure that you get there. But this concludes this problem, and now we're ready to move on to our last example. So let's take a look at our last example in this lecture here. I will not really solve this for you, I leave this up to you, but I want to at least derive the problem for you. So here you have to determine the parallel force component in member BC. So take a look, there's B and C, due to the force FC, which pulls on the pipe structure ABC. So be careful here. This, if you are already advanced in engineering, this can look like you need to do much more than what we're asking here of you. But really what we're after here is the force in that pipe BC. So let me mark that for you in red. So here we have a vector, which is BC. And clearly what we want is BC hat, right? Remember that we want to project FC onto BC. So really what we're looking for here is FBC parallel due to FC in pipe BC. So what we need is FBC parallel, which is nothing else than FC dotted onto BC, but now be careful, head, right? So BC head is what we need in this case. So let's derive that vector first, because FC is already given. I don't need to do anything about that. So FC is given to you right here. I don't have to write anything. But we need to derive BC. So first BC. So how do I do that? I need to go from B to C. How do I get there? I actually, don't be fooled. I do not have to go upwards, right? So the 4 here refers to how far you have to go from A to B or from A to C in the Z direction. So I don't have to worry about that. However, I have to go into the positive X direction by plus 1 I hat. And then in the positive Y direction with 5 plus 5 J hat. And then plus 0 K hat. And this is in meters. And so to get my BC hat, I need actually BC magnitude, which is equal to 1 squared plus 5 squared plus 0 squared, and that's square rooted. And you can calculate that to be the square root of 26. And then last but not least, your BC hat is equal to 1 over square root 26 I hat plus 5 over square root 26 j hat. N plus 0, I don't even bother writing that down. But that again is unitless. And now you can use that in your equation right up here. And there's no need for me to bore you with that. If you need the mathematical procedure, you can find that in the previous example. But I encourage you to really think about that. The last thing I'm willing to do for you here is to visualize it for you. So we have a parallel component here, and we have a perpendicular component right here. So this would be FC perpendicular and then FC parallel. Be careful, depending on where the arrowhead points, right? You also have a force that goes in that direction or in the opposite direction. So let me add actually the directions here for you, which here is very similar to what before, but it's not always that case. Sometimes it is actually not pulling, right? So here it's explained to you because it's the first educational problem, but sometimes that's different. Be careful about that. Understand that we have the right angle here, and also understand that here you have a negative number. It's pulling in the negative x direction. So that means that you have to watch out for your combination of your dot product here when you do FC times BC. But again, the goal here is not to run the numbers for you now. I think the problem has been deciphered. You can definitely now go ahead and solve this and use it as a practice problem. I wish you good luck with that. I think it's time to move on to our last page in the lecture and check our boxes. So now that we've been through our lecture, I encourage you deeply to think about what you took away and what has been new to you. What did you learn really? But more importantly, ask yourself critically, what is the stuff that you did not understand? That is very important to me as your teacher, that you really think about that, because thinking about that will actually clear up some questions that you have. And if not, it will at least help you to understand where you have to go to find more information about this. So please go through that effort. This is by far the most important thing in each lecture, or at the end of each lecture. Don't skip on these 5 minutes that those boxes cost you. That is very important. I put a lot of effort into these just for your benefit. So please use them as such. All right, so what have we learned? We definitely learned the formulas and the operational laws. We don't have to worry about those anymore. Those were derived. We can now use the scalar product, which from now on we don't call dot product anymore, properly. So we can use that and check that off. Then I believe I gave you some examples of the physical interpretation. So please keep the physical interpretation in mind. And what I mean by project vectors onto another. That is our takeaway from this lecture for sure. We also saw the importance of unit vectors, especially in the context of projecting vectors onto another. So we can use the unit vectors properly, and we can describe any vector by its unit vector and its magnitude now. That is a check as well. Very important from an engineering standpoint and for your future career is to really deeply understand this fact that there's always a parallel and a perpendicular component if a force is acting on the structure. And what we did today is really to break those components down, right? So they can always be broken down into the components that we ultimately defined for you or found with you in these problems, example problems that we've been through. So that is important that you understand when there is a parallel and a perpendicular component, or more precisely when you wouldn't have a parallel or a perpendicular component. So in other words, you understand the physical interpretation now of the scalar product, and you can use it to determine the parallel force components. That's really what we're doing here, the parallel force components. That is a problem that you will see on your exam, no question asked. So please make sure that you truly can check this off. And with that said, I believe we completed our last page of the lecture script and we can move on to our homework problems. So let's take a look at these fun homework problems, and of course we go through them one by one. You will be very surprised how easy your very first problem is. What you ask here is to find the force that is parallel in AB due to the force F4 acting at A here. And if you really think about this, you may not have to do any fancy math. If you use common sense, you might arrive at the answer much faster than using what we've done in this lecture. However, you should obviously practice what we did in this lecture to confirm your findings and to be prepared for the method that we will ask of you in the exam. But this is a very simple problem if you think about it. If you just want to apply a method, then it is neither complicated nor easy. It's just a regular dot product problem. So please think about this problem before you start it. And you should always do that, obviously. Don't just, start because you start. Think about implications and what it means. All right, now here we have a similar problem or a similar pipe structure that we saw before in our example. And now the force is not given to you as ijk. That's actually the only difference here for this problem. You need to find the ijk component of F3 first. This practices our understanding of the 3D angles so that you can use the ijk component of F3 to find the parallel force component in BC. So once you found that, it's a very straightforward problem, and I wish you good luck with that. No tricks here, nothing to worry about. So here for problem C, first of all, let's look what the problem wants. It says that we need to calculate the force component along OA, so no surprise here, due to the force F4 in kips. So if you are not familiar with kip, that stands for kilo-pound, right? So kip, kilo-pound. But technically you could solve this without the units, but you're encouraged here to use kips. And F4 is in kips with angles given to you here. And be very careful because this dashed box here shows you that this moves into the negative x direction. So the pipe goes into the negative x direction and the force is also going away from that. In fact, you can see here this line is parallel to the y-axis. And because that's parallel to the y-axis, you see that 30 degrees actually causes the force to pull away from the positive x direction. So please be careful with the negative terms here. But other than that, I believe it is a simple dot product problem. Last but not least, we have a very interesting problem here in which you are supposed to find the angle actually. So you can use the other concept of the dot product that was mentioned to you in the lecture, where you have position vector 1, or it's actually a force in this case, but it's really a position vector, and a second position vector. They have a certain angle between them in 3D, of course. And you can find that angle by using the dot product. Now you see that the first force here is actually given with the directional cosines, whereas the second force, or actually the first force here, F1, is given by this 3D interpretation of these angles. And you can use those to determine the ijk components for F2 as well, and then you can find theta through the dot product. And I believe that concludes our homework overview. You should definitely be able to solve this now with the information provided in this video. I wish you good luck studying and preparing for your quizzes and exams through the homework. If you have any questions on the homework problems, please post them in the discussion boards online. Until next time, stay safe.